To review for all of Unit 4, obviously we're not in our traditional classroom right now, but I thought it would be helpful to kind of go through each page of the Cornell notes and just talk through it a little bit, touch on some topics that are important, and obviously I'm going to skip over some stuff, but if you want to follow along with your notes, feel free. So, just quick review. Electrons always have negative charge, protons always have positive charge, and electrons are the things that are free to move, which is very important. And then these are related because they have the same charge, opposite sign, which is known as an elementary charge. And one elementary charge is 1.6 times 10 to the negative 19 coulombs, which is a very important number for us moving forward. Now, positive objects do not gain protons or lose protons because remember, protons are fixed. They cannot move. So positive objects are going to lose electrons, and negative objects are going to gain electrons. We talked a little bit about charge. Let's move on to transfer of charge. Remember, there is a law of conservation of charge, meaning charge cannot be created nor destroyed. And charge is always conserved as long as it's a closed system, which basically all the examples we're going to look at and have looked at have been closed systems. So if we think back to a way to detect charge, we have an electroscope. And let's say we have a positive, a negative. So 3 and 3. Now, if we bring a neutral rod near it, nothing will happen. But if we take that rod and we apply contact to it with fur, the rubber rod, so let's make sure we know this is rubber, and fur will take electrons from that fur. And rubber is a good insulator, meaning charge can just sit on there. And then when we bring this negatively charged rod near the electroscope, the leaves are going to spread out because the negative charges do not want to be anywhere near this negatively charged rod, which would leave a net positive charge on the knob of the electroscope. And remember, this does not mean that these protons are moving or anything. It just means that since the electrons moved away, it's polarized and that their charges separate and there's a net positive charge on this rod. And then we could also come into contact once we have a negatively charged rod. If we come into contact with this knob, now charge is free to transfer and it wants to spread out. Therefore, now the electroscope has a negative charge. We could also, remember, in conductors, charge wants to spread out as far as possible. So if we have, let's say, two spheres, let's say we have 8, a positive 8 charge, and a negative 16 charge. If we were to bring these two into contact with each other and then separate them, charge wants to spread out as far as possible. So our total charge here is 8 plus negative 16. So no matter what we do, our total charge has to be negative 8. Now, when two metal spheres come into contact with each other, it can separate. And then we separate them. Charge wants to evenly distribute or spread out as far as possible from each other. So now we're going to have negative 8 distributed evenly over two spheres. So each sphere is going to have a charge of negative 4 elementary charges. Charge is, well, not only is it a scalar, but charge is quantized. which is very, very important to know for this unit. So charge is quantized. And what does that mean? That means that there can only be discrete packets or a certain number of electrons or a certain charge. So we can have, let's call it electrons. We can have one electron. We can have two electrons. We can have three electrons. We cannot have 1.6 electrons. That does not work. So that means our possible charges could be negative 1.6 times 10 to the negative 19 coulombs. We could have negative 3.2 times 10 to the negative 19 coulombs. We could have negative 4.8 times 10 to the negative 19 coulombs. These are all negatives. But we cannot have negative 1.8 times 10 to the negative 19 coulombs. That does not work because our charge always has to be divisible by an elementary charge. So it has to be divisible by this number. Okay, next thing we're going to discuss is Coulomb's law. And Coulomb's law, most important thing, it is that it is the not only the force of attraction between two charges, but it's also could be the force of repulsion, where again, it's worth me saying for the probably 10,000th time this year, but force of gravity is always attractive, but the electrostatic force can be attractive or repulsive. And that's given to us by this formula. And we can manipulate it in any way we need, but as the amount of charge goes up, the electrostatic force increases. If we increase the distance between the two charges, then the electrostatic force would go down. All right, electric fields. We draw electric field lines with arrows, therefore we know it has to be a vector quantity. Electric field strength is given to us by the electrostatic force over the charge at a specific location in space. And remember, electric field lines always go out of a positive. If we think back to our acronym that we used during this course or during this little unit, what would a positive test charge do? So if we place the little positive test charge right here, it does not want to be near this positive, therefore it would move away. So the electric field lines always point away from a positive. If we have point A and point B, well, the electric field strength is greater at point A because the lines are closer. So the closer the lines, the stronger the field. Remember, these lines can never cross. So go out of positive and they go into negative. So here if we have oppositely charged parallel plates, which hopefully some of you go on to study physics in college and you'll learn about capacitors, but the electric field lines always go from positive to negative. An important thing to remember for oppositely charged parallel plates, the E field is uniform in between these plates, meaning that no matter where I am in this electric field, I'll always experience the same electrostatic force. And if I were to place an electron in here, well, it doesn't want to be near these negatively charged plates, so an electron would move towards the positive plates, and the opposite effect, if I placed a positive charge over here, it wants to move with the electric field lines and go towards the negative plate. Okay, probably the formula that we use the most in the electricity and magnetism unit is Ohm's law, which is given to us by R equals V over I. Resistance equals voltage over current. And we measure current with an ammeter. And we measure voltage with a voltmeter. Remember, voltmeters are always connected in parallel. And only electrons are free to move when we're talking about, current in a circuit. And important graph to know is the relationship between current and resistance, or resistance and current. So if I have potential difference and the resistance of, something is staying the same, well, as current goes up, the potential difference will also go up naturally. Now, the slope of this graph, if we do change in y over change in x, that's equal to, well, here we have voltage over current, which is equal to resistance. Other thing to remember when we're talking about resistance is, think of the word resistance. It resists current flow. So if we have a high resistance, well, we're going to have a low current flow, or a low reading in that ammeter. Now, we're talking about the resistivity of wires. There are four things that affect the resistivity of a wire. The first is length. Measure that in meters. Second is the cross-sectional area, which is meters squared. The third is, that's a bad one, Greek letter rho, which is a property of that wire. And the last one, which again we're probably not going to be assessed on, is temperature. So the higher the temperature, the more resistance or resistivity of a wire. So if we want to have a low R, we want a really short wire, a really thick wire, a high cross-sectional area. We want it to be silver, but that's really expensive, and we want it to be very cold. All right, so there is conservation of charge in circuits, and we have these points called junctions. And basically, reviewing this, the current in to the junction has to be equal to the current out. So let's say we have 4 amps going in, we have 3 amps going out, and let's say we have 3 amps going out on this side as well. Well, in this junction, the way it is right now, we have 6 amps out and we have 4 amps going in. Therefore, to balance this out, in order to make this work, well, we have to have 2 amps going in. And let's say this one, let's say we had 7 amps going in and we have 1 amp going out. So as this stands, we have 7 amps in and we have 1 amp out. But in order to balance that out, we have to have 6 amps coming out of this junction. Talk a little bit about the two types of circuits and a little bit about the meters in these circuits. If we were to connect an ammeter, for series it doesn't matter where we put it, but we do have to put it in series. So it has to be where all the current will pass through it. And in a series circuit, all of the current is the same no matter where we are. And if I wanted to figure out the voltage for the entire circuit, I could put a voltmeter across the battery, having it on each side. Or if I wanted to measure the voltage across one individual resistor, I could place it across like this. Remember, like I said, the current is the same no matter where we are. The voltage will be different. So the voltage of the battery is going to be equal to the voltage across R1 plus the voltage across R2. They'll add up to the voltage of the battery. And the resistance, total resistance or equivalent resistance, is equal to R1 plus R2. Remember, ammeter is always connected in series, voltmeter is always connected in parallel. And if we have, quickly, we'll talk about a parallel circuit. Biggest difference and thing to know is a parallel circuit is where current splits. So here we have R1 and R2. Now, I don't really need to place a voltmeter in this circuit. I could place it here, but I don't need to because the voltage is the same no matter where I am. So if this is a 12 volt battery, well, this would read 12 volts. Add up the resistors a little differently. We use the inverse. So the equivalent resistance is 1 over Req plus 1 over R1 plus 1 over R2. And look back at my little calculator trick to help you figure that out. We still place the ammeters in, place 3 of them. If we want the total current in the circuit, this would give us the total current. Let's say it's 5 amps. Now, this could be a switch, so if we close this one, this would read 5 amps right now because no current's going to go through R1 because this is not a closed circuit. Remember, it has to be a closed circuit for current to flow. And if this one were to read 2 amps, then this one would read 3 amps because they have to add up to the total current. So in a parallel circuit, the current splits and the total current is equal to I1 plus I2. Okay, so we can manipulate Ohm law if we need to figure out the electrical power equal to VI, I squared R equals V squared over R. And if we think back to our energy unit, remember, in order to have power, you have to work over time. We can rearrange this, so P times T equals work. So any one of these power formulas times time gives us the electrical energy in a circuit. So we get a VIT equals I squared RT equals V squared times T over R. And we can manipulate any of these to figure it out. Okay, the last thing in this review video will be magnetism, which we just introduced the other day. And in order to produce a magnetic field, remember, it has to be moving and charged. So an electron will produce an electric field if it's stationary. If we move that electron, it will produce a magnetic field. A neutron will not produce a magnetic field even if it is moving. And remember, magnetic field strength is just like gravitational field or electric field, where the closer the lines, the stronger the field. And remember, they are south-seeking, so the lines would go out of the north and into the south. And if we were to take a conductor, let's say we have these lines going here, and I place a conductor right here. In order to produce or induce a potential difference, I need to move that conductor across the magnetic field lines. I have to make sure they're physically crossing those imaginary lines in order to induce that potential difference.